This problem says, from scratch, prove that the polynomial ring z attach x is Noetherian. In particular, you may not use the Hilbert Basis theorem. Okay, so we're gonna take a sort of liberal interpretation of the directions here. Um, so the Hilbert Basis theorem says that if R is a Noetherian ring, then R attach X is a Noetherian ring. And then, of course, that generalizes to any number of variables by induction. Um, but so Z is a right. So to be a Noetherian ring means that you are a Noetherian module over yourself. Uh, and to be a Noetherian module means that every ascending chain of submodules stabilizes, or equivalently, that every submodule is finitely generated. Since we're talking about a ring over itself, submodules can be equated with ideals, and so we need to prove that every ideal of this ring is finitely generated. So uh, it is true that Z is a Noetherian ring. Um, the ideals of Z are of the form NZ, where N is some natural number. Um, and in particular, those are all generated by N, which is not just finite, but in fact cardinality 1. So uh, Z Z is a PID. So that's um, uh, even better. But since I'm not totally sure how to um, prove this quote unquote from scratch without invoking the essentially reproving the Hilbert Basis theorem, we're just going to essentially prove the Hilbert Basis theorem. So we're not going to cite the Hilbert Basis theorem, but we're going to prove it um, in order to get this result. Um, Noting that Z does have some additional structure beyond just being Noetherian. So in particular, it's a PID. So maybe maybe there is a um, maybe there is a better way to prove this more directly. But in any case, this still ought to be quote unquote from scratch. Um, so uh, and use while we will talk about Z attach X, the proof clearly, as we will see, could be just since that's the context we're in, the proof could be generalized to Z being any Noetherian ring. Okay, so the proof is we'll show that every ideal I of Z touch X is finitely generated. So let I be an ideal. And now we will let F1, so we're going to use some uh, amount of the axiom of choice here. So let F1 be an element of least minimum degree in I. Uh, let F2 be an element of least degree in I take away the ideal generated by F1, right? So we're just choosing some polynomial of minimum degree in the ideal I. That's our F1. There could be many of that same minimum degree, but we'll just choose one. And then we get some ideal generated by F1, which um, uh, and if it's not all of I, then we get to choose an F2 that is an just some polynomial with least degree amongst those in I, but take away the ideal generated by F1. Um, let F3 be an element of least degree in I, take away the ideal generated by F1 and F2, and so on. So essentially what we mean is uh, right, that Fi is some polynomial of least degree in um, amongst those in the ideal I, but not in the ideal generated by F1 to F2, F3, all the way to Fi minus 1. Um, so first of all, note that if we ever run out of options, right? So if for some I, uh, the ideal generated by F1, F2, all the way up to Fi is actually equal to I, and therefore we couldn't keep going, well, then we're done because we've shown um, I is finitely generated. So um, we might as well assume that we do get an infinite sequence. Um, F1, F2, F3, and so on. And now let's let AJ be the leading coefficient of FJ. And then let's look at this ideal. So let J be the ideal generated by all of the AI, the AJs, A1, A2, A3, and so on. Uh, Infinitely many of them in the interesting case. Okay, but then the key thing is, well, actually, they're not infinitely many of them, or there don't need to be, because, well, the coefficients they all come from the ring, right? They come from Z in our case, and so uh, this is an ideal in Z, and Z is Noetherian. In fact, it's PID, uh, but it's Noetherian. So um, um, just to give the proof in full generality for the Hilbert Basis theorem, we'll just use that it's Noetherian. Um, so then. J is an ideal in Z, and since Z is Noetherian, J is finitely generated. Okay, it's actually J is actually a principal ideal, but we don't need to worry about that. We can just say it's finitely generated. Um, and um, moreover, right, so there's some finite set of elements that generates this ideal J. And that finite set, well, they're all in J, so they're all um, some finite linear combination of uh elements of these AJs, right? And so in particular, whatever that finite generating set is, well, there's some uh we can, sort of replace it um with some initial segment of these AIs. Right? So not only is J finitely generated, it actually has to be finitely generated by A1, A2, A3, all the way up to AM for some M. Um, so let M be the least integer such that J is equal to the ideal generated by A1, A2, AM. Right, okay, there might be some redundancy here, but that doesn't matter. Um, so now then actually our goal is to show that I is finitely generated. So actually we claim that the core, so we have A1, A2, AM, these are the leading coefficients of F1, F2, Fm. So we actually claim that I will be finitely generated by F1, F2, and so on up to Fm. So if I is equal to this ideal, the ideal generated by F1 to Fm, then in particular I is finitely generated and we're done. Okay, so let's show that, uh, or again, 1 through M come from this corresponding 1 through M. Okay, so let's prove that I is equal to the ideal generated by F1 to F2, all the way up to F. Okay, so if um, the ideal generated by F1, F2, all the way up to Fm is a strict subset of I, then we can make another choice. We can choose some Fm plus 1 with least degree among all elements of I, but not the ideal generated by F1 to Fm. Um, okay, so recall that AM plus 1 is the leading coefficient of our Fm plus 1. And now, since um, Well, okay, so just perhaps we shouldn't say it's not like we're choosing again. So it's not that we can choose that we chose in what we already did. We chose some fm plus one with least degree amongst all elements of I that are not in the ideal generated by f1 to fm, f1, f2, fm, so on. Okay, so am plus one is the leading coefficient of fm plus one. Um, and uh, since am plus one is an element of J, and J was initially defined to be the ideal generated by all of the leading coefficients, A1, A2, A3, da, 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 da. That's how we know that am plus one is in J. But then J was later discovered by uh, Noetherianists to be the ideal generated by A1, A2, up to AM. Uh, right. Um, we know that AM plus 1 is some linear combination of these A1 to AM. So sum from J equals 1 to M of some UJ AJ. Um, where the UJs are um, uh, some element of Z or of the underlying ring, whatever that is, if we're doing this in more generality. Um, okay, so let's also uh, let's uh, define now a polynomial G that is the sum from J equals 1 to M of UJ times FJ times X to the degree of Fm plus 1 minus the degree of Fj. Okay, so first of all, we have to check this is a valid definition of a polynomial, but it is because of our construction. So, in particular, the degree of Fm plus 1 is going to be bigger than or equal to the degree of all of the Fj's for J from 1 to M. And that's because in our construction, right, F1 was the some polynomial of minimum degree in I, and then F2 was some polynomial of minimum degree in I, but not in the ideal generated by F1. So in particular, it has to have at least the same degree or bigger, um, and so on. Uh, so um, this is always non-negative, and thus this is a valid definition of a polynomial. Um, so this is valid since the degree of Fm plus 1 is greater than or equal to degree of Fj for all uh, j in 1 through m. Okay. Uh, and now, well, let's look at the leading coefficient of g. Well, so what's happening here is that we're making the degree of um G uh equal to the degree of Fm plus 1 because um whatever it is that we start with um we uh we just add enough copies of X to force the degree to be the degree, whatever the degree of Fm plus 1 is. Um, and um, moreover, well, what's the leading coefficient? So, no, the leading coefficient of G is sum from J equals 1 to M of U, J, AJ. And uh, that's because AJ is the leading coefficient of our FJ. And so um, we just add up all of the UJs times the F times the coefficient of this FJs, and that gives us the leading coefficient since all the terms here have degree uh, equal to the degree of Fm plus 1. Um, so which is the same as the leading coefficient Am plus 1 of Fm plus 1. Right? Am plus 1 is equal to this sum as well. Um, and also, as we said, um, the degree of G is equal to the degree of Fm plus 1 by how we define G. Um, so now let's note that Fm plus 1 and G are in the ideal I. Uh, Fm plus 1 certainly is, and G is some linear combination of F1 to Fms, which are all in I, so it's also in I. And so, I is an ideal, so it's a additive group, and so we can subtract and still get something in I. So Fm plus 1 minus G uh, is also in I, but Fm plus 1 minus G is not an element of the ideal generated by F1, F2, up to Fm, since uh, G is by how we define G. Um, so if Fm uh, so if Fm plus 1 minus G were then Fm plus 1 would be, right? If it were an element of this, then Fm plus 1 would also be an element of this because G is, so you could add and see that Fm plus 1 is. So, but of course Fm plus 1 isn't. Um, but now, since Fm plus 1 and G have the same degree and the same leading coefficient, when you subtract Fm plus 1 minus G, um, has degree strictly smaller uh, than the degree of Fm plus 1, right? We subtract something with the same degree and the same leading coefficient, then we're going to get something with a uh, smaller degree. But this but we just said that Fm plus 1 minus G is in I and not in is in I but not in the ideal generated by F1, F2 up to Fm. And so this contradicts uh the fact that we had chosen Fm plus 1 to have minimum degree among all elements of I, but not the ideal generated by F1 to Fm. And that shows that gives a contradiction, so that shows that I actually is the ideal generated by F1 to Fm, and thus in particular I is finitely generated. And so uh, Z join X, or more generally R join X, where R is any Noetherian ring, is in fact a Noetherian ring.